as you talked about during the lecture, correlation suggests what it suggests in English, an association between two variables. For starters, what kind of variables are we talking about? I'm not sure that came up, but obviously, what kind of variables do we deal with that we need to deal with? Okay, if we're dealing with correlation, for instance, in this situation, I'm trying to determine if there's an association or correlation between a person's age and their average blood sugar. For instance, these are say 10 individuals and their average blood sugar measured over a period of time. And I'm wondering, is there an association as people get older? Does their blood sugar go up or go down with their age, and so on and so forth? Okay, so I'm looking, yeah, the numerical variables. Very good. Thank you, Julian. Okay, so we're almost always working with two variables, right, bivariate, and we're always working with two numerical variables that we're looking for an association with. Okay, so I'm gonna pull up these numbers, posted into an Excel file instead of displayed on in this Word document, and this is what we might be dealing with at this stage. Okay, here's the age of each individual, and there's the average blood sugar level. So, one of the ways that might be my first approach to seeing if there's some kind of association between these two variables is to plot them graphically. Okay, and one of the ways I may look at this is I'm going to insert a row over here. I may look at this as two associated values, an x value and a y value, and I might plot this on a graph, for instance. Okay, so I'm going to call one of these x. I'm going to call the other one y. Now, when we're talking about associations, okay, when we're talking about correlation, we really don't care which one that we call X and which one that we call Y, because we're just trying to demonstrate there's an association between these two values. As one goes up, the other goes down, if they really do change in that way, or if there's no association with them, and so on and so forth, right? So we're not really that concerned at this stage which one is X and which one is Y. However, later on, when we talk about regression, then we're going to talk about causality. In other words, does a person's advancing age cause their blood sugar to go up, or does a person's elevating blood sugar cause them to get older? Well, obviously, the causative variable here is age, and the result is blood sugar. And we define formulas as a function of x is equal to some formula, or instead of function of x, frequently we use y in place of function of x. Okay, y is equal to some function of x. Okay, so y is determined by the value of x. Okay, so usually the independent variable, the one that is causing the other one to change, is in the x axis, and the dependent variable, the one that's being changed by the other or determined by the other, is in the y-axis. That's usually the way we like to plot them. Doesn't matter for what I'm doing right now, but in the long run, it's going to be easier if I just kind of stick to, plotting them this way. So now, basically, for each one of these pairs of values, they represent a point on an xy coordinate. In other words, person's age is 30 and their blood pressure is 75. X is 30, Y is 75. X is 34, Y is 90. X is 36, Y is 65. Okay, well, I can easily just take a graph and plot this on a graph. In fact, I'm going to use Excel to do that for me. I'm going to highlight these two columns and their associated values, and I'm going to go up to the charts. And the kind of chart that I'm interested in displaying is a scatter chart. I'm going to take a simple scatter chart, which is just going to plot these different dots for me on a XY coordinate. Okay, I could do this manually, or I can use Excel to do this for me. And here we go. Okay, here is Excel has plotted these values for us. Okay, and in fact, you can actually figure out which of these individuals each one of these values represent. The youngest person is about 30 years old, and his blood sugar is about 75. You can see that is the point that we plotted there, and so on and so forth. Okay, so now, if we're looking at these, we notice that as a person's age advances, his blood sugar also tends to get higher. It's not a perfect association. Yeah, this person was 44 years old, an average blood sugar of 110. This person was older. He was 48, had an average blood sugar of 80. Now, of course, these numbers are all made up just so that we can demonstrate this association. Okay, so now if I were to attempt to draw a line through these that would best approximate this relationship, it probably wouldn't actually hit any of these individual points, but I could draw a line that kind of suggests what the relationship between blood sugar and age and blood sugar is. Okay, and if I extended that line, I could actually see that line go all the way back here and cross the x-axis. I'm going to kind of imagine this going down here, and I'm going to think, gee, it kind of looks like it crosses the y-axis here, and it crosses the x-axis down here at, say, minus 20 or something like that. Do you guys see that? That, like, if I extended this line, it would cross the x-axis at about minus 20, right? It would cross, no, excuse me, the y-axis at about minus 20. Of course, that's meaningless, isn't it? There is no such thing as a blood sugar of minus 20. That doesn't mean anything, right? Just like there isn't an age 0 that you would be able to do this, right? But one of the valuable things about knowing where this crosses the y-axis is that I can define any line by where it crosses the y-axis and what its slope is. So in other words, if I have a line that crosses the y-axis at 20 and has a slope of 1, in other words, for every 20 for every 10 it goes up 10. For every 10 it goes up 10. That's the slope. I can draw that line. If I know the point where it crosses that axis and the slope, I know that line. Okay, if I were to say it crossed at 30 and had a slope of 9, well, that line would have a much steeper slope, but it would cross that y-axis there. If I said it had a y-intercept of 100 across the y-axis at 100, and it had a slope of minus 5, well, that would slope downwards. As the x value went up, the y value goes down. It's negative. Okay, so that would be sloping downwards. So I can always describe a line by telling you its y, where it crosses the y-axis, even if that's a meaningless number, and what its slope is. Slope's important because the slope tells me how fast it goes up. So if I look at this chart here, well, this is as age goes up, blood sugar goes up. But now it's important to me to know how quickly does blood sugar go up. In other words, if blood sugar goes up very fast, then I know age is an important factor that I have to take into account. Now, but if this is relatively flat and as people age, their blood sugar doesn't go up very much, well, that slope tells me that I don't have to be too concerned about advancing age being a factor in high blood sugar. Okay, so, but maybe this is in between somewhere. Okay, so this is that. Looking at this graph tells us a couple of things. Tells us how good a correlation there is between these two variables. It tells us whether that correlation is positive as one goes up, the other goes up, or negative as one goes up, as age goes up, blood sugar goes down, the y goes down, or and how good that correlation is. Well, now we're going to calculate a number that tells us estimates for us how good a correlation this is, and this is the correlation coefficient. Okay, now I'm going to do it very quickly first time around. I'm going to use Excel to calculate it for me. There is actually a function built into Excel. Correlation, I'm going to call that correlation coefficient R. That's going to be equal to correlation, parentheses. It asks me for array 1 and array 2. In other words, the x values, comma, and the y values. I'm going to hit enter, and the correlation coefficient is equal to 0.82. Based on what you heard in the last couple of hours, is that a very good correlation? What can you tell me about that correlation? Rather than turn on voice and stuff like that, I'm going to depend on you guys to type it into the questions box. Okay, what can you tell me about the? Oh, yeah, it's a strong correlation. Everybody agrees with that, right? This is a pretty strong correlation that we're dealing with. Okay, so now it's a strong correlation. It's also it's close to one, right? If we're zero, it would be almost no correlation. Now, what about the fact that it's a positive number? What does that tell us? Right? It's positively correlated. In other words, as one value goes up, the other value also goes up. Had it been a negative 0.82, then that would have told us it's a very strong correlation, but it's an inverse correlation. As one thing went up, the other went down. Right? Now, just again, this is a situation where it's reasonable to assume that there is some causality between age and blood sugar. That's not always the case when you're dealing with correlation. I'll give you an example. What if I told you that the number of firemen is positively responding to a fire is positively correlated with the amount of damage in the fire? Does that mean that the firemen are causing the damage in the fire? Okay, what does that tell you? That like if a lot of firemen respond to a fire, means there's more damage. Is there really an association between the number of firemen and the amount of damage that a fire causes? Right. Well, there is an association, right? But it's not a causal association, as Michael pointed out. Okay, it's an association because you're going to get more firemen to a larger fire. They're going to call more companies out and so on and so forth. But the reason for that, there's a different reason for those things to be correlated. The size of the fire is determining both of those things: the number of firemen responding and the amount of damage that's being done as well. Okay, so there's something that we have an association, but it's not a causal association. Okay, good, great. You guys got the right idea on this stuff. Okay, so now I'm going to actually calculate that R value because it seems to me that I got a strong suggestion. One of the things that's valuable to do as a student is whenever a professor suggests, yeah, this would be a really good question on an exam, that you listen to him and like you get ready for like maybe seeing that on an exam. So we noticed that Professor Yang mentioned that, gee, calculating the correlation coefficient is probably something that you'd be able to do if you did it on if you came across it on an exam, because it's a relatively simple calculation, or at least something that you can do with a calculator or with Excel and so on and so forth. Okay, so we're going to run through that, see if we wind up getting the same value as we calculated using Excel. Okay, so first thing I need to do is I have to calculate X bar, because my first column here wants me to calculate each individual X value, Xi, minus X bar, the average for the X values. That's going to be equal to average for all these X values. That's my X bar. And I'm going to need my standard deviation for my X values as well. Good. Okay, and I'm going to need the same thing for my Y values. I'm going to just copy it across so I don't have to put those formulas in again. Whoops, I did that wrong. Fill right. There we go. Okay, so I got the mean now for X. I got the mean for Y. I got the standard deviation for X, standard deviation for Y, and I'm going to be able to calculate all these values at this point. So this is going to be equal to the X value, that my first individual X value, minus my average X value, which is going to be this value. Now I want it to repeat that value over and over again. So I'm going to make sure it references that cell exactly and doesn't move around. Okay, like so. I'm going to put that inside of parentheses. Okay, and I'm going to divide by the standard deviation for X. I'm going to hit enter. And that's that value for that particular value. Going to copy this down, fill down. Okay, oops. What did I do wrong there? I forgot I had to do the same thing with my standard deviation, didn't I? Okay, I have to put a $ in there. a dollar sign in there so it doesn't copy it down. Maintains the same value there. I'm going to edit and fill down. Okay, so now I'm going to do the same thing for my y values. Okay, you guys following this? Equals. Okay, it's going to be equal to my y value minus my average value for y. I'm going to put that in parentheses and make it an absolute reference with the dollar sign so it doesn't move down as I copy the formula. Divided by my standard deviation. And again, I don't want that to move down. Dollar and dollar sign in front of the number of the cell, enter, and I'm going to copy that down as well. Okay, now I'm going to multiply these two together is equal to my differences minus over my standard deviation times for x and for y. And I'm going to fill this down. Okay, and I'm going to add all of these up. Sum. Okay, comes out to 15. Now, what are my number of degrees of freedom? My number of degrees of freedom are, any guesses on that? Number of degrees of freedom? How many numbers we have here? We have 10 numbers, and we have 9 degrees of freedom, right? So our R coefficient, R, is going to be equal to our sum divided by our degrees of freedom. It's going to, oops, did I do something wrong there? I did something wrong there. What did I do wrong here? What did I forget to do here? Let's see. Degrees of freedom is 9. R, there's something wrong with this value here. Let's see. Minus 2. Let's see. Minus 3. Okay, let's see. Standard deviation. Let's see. 14. 14 and oops, that's the same number, isn't it? Something went wrong there. That's 14. This should be 15. This should be B. Good spot. B. Put a dollar sign. Put a dollar sign. Let's see if this works out better. Okay, edit. And fill down. Up, there we go. That's a little bit better. Thank you, Sonali. You're the first one to pick that error out. Okay, and in fact, my R value, my correlation coefficient, is the same value that we round up when we use the function that SPS has built in. Okay, we're actually going to be able to do that if we want using SPS as well as, in fact, we're going to go through a couple of calculations that involve that. Okay, so this suggests that there's a relatively strong correlation between these two variables. Now, I'm going to repeat these calculations using SPSS. I'm going to work with another variable for SPSS. I'm going to post this later on. This will actually outline for you the sequence that you go through in SPSS to find these various calculations. But we're going to take a look at this and actually do it right now. Okay, first one I'm going to take a look at is an example of temperatures in different cities. Okay, here's a number of different cities around the United States, geographical groups, so on and so forth. Their average annual temperature, the latitude of the city, and the longitude of the city. Okay, so I kind of think that there's a pretty strong likelihood that the latitude of the city, how far north the city is, has something to do with its average temperature. Okay, we know it's not the only thing that has to do with its average temperature, right? There may be other factors involved. We're going to talk about that in a second. So I'm going to go up to, first thing I'm going to do is I'm going to plot this graphically to see if there, I think these are, I'm going to plot these graphically to see if there's an association between these, because we know that that's always a good way to start. Well, SPSS has a number of ways to plot these charts. One is it has a built-in chart builder. It has a template that you can use, kind of a wizard, and it has a legacy dialog, which is really simple, an older way of doing it that from its original versions. And since we're just interested in a scatter plot, I'm going to use this legacy dialog. I'm going to go legacy dialog, scatter dot, click on that. I'm going to tell it I want to do a simple scatter plot. And a simple scatter plot is just going to ask us for our x-axis and our y-axis. So if I'm looking at latitude and temperature, okay, again, if I'm just looking at correlation, doesn't matter which one I put in the x and the y-axis, I'll get the same R value. But if I'm later on going to be interested in trying to use one of these to predict the other, then I'm going to want to put the independent variable in the x-axis and the dependent variable, the one that's determined by the other, in the y-axis. Which one do you think should be the x-axis then, latitude or temperature? I'm sure you guys have an opinion. Okay, I got a difference of opinion here. Okay, well, I'm thinking that the thing that causes latitude. Well, let's see. This is a pretty good question, right? Well, temperature is not going to cause the latitude to change. Latitude is a physical place on Earth, but the latitude may have some influence on what the average temperature is. So I would say latitude is my x-axis, right? And my independent variable is temperature. Okay, temperature, temperature could be a predictor of latitude. Average temperature could be a predictor of latitude, but I don't think temperature is going to cause latitude to change, where the latitude may cause the average temperature to change. Okay, does that make sense to you guys? Okay, I'm going to call the x-axis the latitude, okay, as a predictor of average temperature. Okay, so I'm going to go ahead and say okay. And SPSS automatically graphs this situation for me. Okay, things are a little bit different this time though, right? Let me take a look at this. Here's the latitude. As the latitude increases, as we get further north, what happens to the average temperature? Well, it looks like there's a correlation here, right? Because I can see that there's some association here. As latitude goes up, temperature changes with it, right? Except this time, instead of being a positive association, it's a negative association, a negative correlation. Okay, so one of the ways that I can take another look at this is I'm going to double click this. It pulls up a little editor for this chart, and I can actually ask it to draw a line. See, it did it automatically as soon as I brought up the chart builder. Okay, I can ask it to draw a line which approximates the line representing the regression, the best fit line between the latitude values and the temperature values, so that each one of these is the distances here of all these points squared is equal to the distances away from this line for all these points squared. So this seems to be pretty much the best fit for this particular relationship. Okay, so while it did that, it also calculated the R value. In fact, it calculated a value called R squared. Okay, R times itself. Okay, well, I'm going to hang on to that. This is interesting. It seems like a pretty good correlation. And R squared is equal to 0.68. So I know that that's going to be a number, since it's a fractional number R all the time. I know that R is going to be even bigger than 0.68. So it's a pretty good correlation. But I don't have to depend on this to figure that out. I can actually use a SPSS to say analyze, correlate, bivariate, because we're using two variables. And I can ask it, notice when I do this, it doesn't ask me for which is the x-axis and which is the y-axis. It just wants to know which of the two variables. I'm going to click OK, and SPSS calculates the R value for me. And in this case, the R value, Pearson's correlation or R value, is equal to negative 0.83. Similar to the example that we had before, same kind of correlation, but this time the correlation is a negative correlation. As one value goes up, the other value goes down. Okay, so we can actually calculate this correlation. Remember that R square that you saw there before? That R square comes from negative 0.83 times negative 0.83. It happens to be positive 0.68. That's going to come up in a few moments because we're going to take a closer look at this. Okay, so now, I found that, there seems to be a positive correlation here, right? Excuse me, there seems to be a significant correlation here. Significance is very good. Seems to be a real correlation here. There's an association between latitude and temperature. Well, what about cities where I don't have information on what the average temperature is, but I can look at a map and see what their latitude is? It would be very useful to have a formula that I could use to predict the average temperatures for cities that I don't have data for based on their latitude that I can look up on a map. Right? So I want to see if I can't create a formula that'll do that for me. So I'm going to go up here to analyze. And this time I'm going to go past correlation to regression. And now I'm going to assume, because of what I saw in that graph that I worked with initially, and because I did that graph and I could see I had a very good correlation, I'm going to go ahead and perform a linear correlation. I'm going to click on that. This time it's asking me which is the dependent variable, that's your y-axis, which is your independent variable, your x-axis. Independent variable determines what your dependent variable is. Your latitude in this case is going to determine what your average temperature is. Okay, so I'm going to go ahead and I'm going to ask it. You can ask it to do some plots here if you want. I'm not going to work with that at the moment. I'm going to just go ahead and say, go ahead and figure that correlation out for me. It repeats our correlation coefficient. Here's our correlation coefficient of 0.83, the same thing that we calculated before using a correlation in SPSS, the same thing that we would have calculated had we done the calculation with these same numbers in Excel, just as we had done it for the previous example that we ran through. Okay, so our R value is 0.83. Okay, now notice it didn't bother to give me a sign there, right? Well, that's because we're going to work that out in a moment. It's going to fill us in on what kind of correlation, whether it's positive or negative. When it does a regression, it doesn't bother giving you the sign at this point, because really it's figuring out this R value because it wants to take it, square it, and tell you that R squared is 0.68. Well, let's call that 0.69, 69%. Anybody remember what the significance of R squared is? Rebecca, we'll take a look at the outliers again when we get a chance to in a second. I just want to make sure we get through this first. Okay, and what's the significance of that 69%? Anybody remember what R squared represents? It represents the percentage of the change in one variable can be accounted for by the other variable. In other words, 69% in the change of average temperature can be accounted for by the latitude. Well, 69%, what about the other 31%? What causes that? Exactly, 69. I like that, Jordan. I like that description even better. Latitude explains 69% of the variability in temperature. Okay, so there's 31% less. What's causing the rest of that variation? In other words, latitude doesn't explain everything. There must be some other factors that are involved here, right? Anybody think of like another factor might affect the average temperature of a city in the United States besides its latitude? What else besides latitude might account for that other 31%? Bingo, Mike. Thanks, Michael. Elevation. In other words, you can have, if you've ever been out in Arizona, when you're down in the valleys and stuff like that, in some cities and stuff. For instance, you're in Vegas, the temperature in the summertime can be 115 degrees. But if you go up to Sedona, it might be 20 degrees cooler in Sedona because Sedona is I think, like an elevation of like 6 or 7 thousand feet. So even though the latitude is about the same, the elevation makes quite a bit of a difference also. So elevation, maybe some other factors, trade winds, or winds, weather patterns, and so on and so forth, mountains, and so on and so forth, might account for some of the amount of rain that they get, might account for that other 31%. In fact, next week, we're going to be looking at something called multiple regression, where we're not just going to look at just one factor. We're going to say, well, gee, it's great that I can account for the average temperature by looking at the latitude, at least 69% of the value of the change in the value based on latitude, right? Maybe I can combine that with other variables also and get an even more accurate a predictor for the average temperature. Okay, so now I'm going to go down here to this box that says correlation coefficients. Okay, now in these coefficients, we see that there are two important numbers here under this B. There's one number that's labeled a constant, which is 110, and there's a second number that's labeled as latitude, which is negative 2.15. Okay, well, I'm going to go pull up a sheet of paper. Let me see if I can't find it here. Notepad, notebook. I'm going to pull up a piece of paper. This is from earlier. Okay, let me get my pad out. Okay, so now we noticed that, let me go back and get those two numbers. Those two numbers were 110 and negative 2.15. Okay, now I had mentioned before that you can describe any line by by y is equal to. Okay, now I'm going to go back to our early math days. Many of you have seen this formula in different forms. The one I'm most familiar with is seeing it as mx plus b. Okay, m was the slope, b is the y-intercept. Well, we tend to use it in biostatistics. We use it as y is equal to a plus bx. Okay, but it's really the same formula. mx, m is the slope, except this time b is the slope. Except this time a is what we would call the y-intercept. Okay, and let me show you why we call it the y-intercept. We call it the y-intercept because y represents our dependent variable, which in this case is temperature. Temperature is equal to a plus, let me just, bx, okay, is equal to my some constant plus the slope times x. Well, in this case, our slope is represented by latitude on our table. You might have noticed that it was labeled as latitude. So our formula says temperature is equal to the constant, which turned out to be 110, minus 2.15 times x, which is the latitude. All right, so this formula represents a straight line. Y is equal to, another way of writing would just be 110 minus 2.15 x, except we know that x is really our latitude, y is really our temperature. Where did we get that from? We got that from our coefficients that were calculated by SPSS. This is our y-intercept. This is our slope. Latitude is our slope. Okay, so let me go back here. So now what does that tell us? That tells us that if I were to draw temperature over here, 0, 10, 20, 30, 40, 50, and this were 110 up here. right? And I were to start at this point, right? Now, if x is 0 here, right? X is 0 here. Let's say it's 5 here. Let's say it's 10, 15, 20, 25, 30, 35, 40, and so on. Well, what's going to happen is starting at that point, our line would go down for every one value in the x-axis, like 1x, it would go down 2.15 in the y-axis. So if I went across 10 in the x-axis, I would be going down 10 times that, 21 and a half. So 21 and a half would be about 90. It'd be about there if I went across here. So my straight line would look something like this. Okay, and if I were to look at all the cities on here, I would get that curve that I just drew. Now, one of the things that we mentioned about this is that a lot of times this y-axis, y-intercept really doesn't have a lot of meaning, right? Because, for instance, remember with blood sugar, we got a 0 blood sugar is meaningless. You can't be alive with a 0 blood sugar, right? So 110, well, we don't have a city in the United States that has an average temperature of 110. Even in the desert, it's 110 in the summertime, but sure isn't 110 in the wintertime, right? So really, our regression really only has meaning within the range that we have actual values. The formula is useful because we can use the formula to predict individual values. But we really should stick to using it only where we have actual values. Now, if I can go back quickly to what the graph looked like, well, we only really had values from 25 latitude 25 to a latitude of 50. So that's really where we're working. It just happens that if you would notice that that this x-axis only goes down to 25, if you were to go all the way back here off the page, back here by this little ring binder over here, then eventually you would cross the y-axis at about 110 way up here, right? But that's not useful to us in terms of viewing it graphically because all of these values are here. So now, or within this range. So now, what does this do for us though? Well, it gives us a formula which represents this line. So in other words, this particular value here for this city, whichever city it happens to be, there's actually a way for me. I don't want to mess with it right now. There's a way for me to actually tell you what that value is. But that particular value represents one particular city that is at an altitude of a latitude of 36 and has an average temperature of about 48 degrees. Where this might be somewhere in North Dakota or something like that, a latitude of 48 and an average temperature of 9 degrees. Okay, this is probably, of course, centigrade. Okay, so this gives us this graph gives us an idea of where we would expect these cities to be roughly. Now, there are some that are pretty far off this line, like for instance, this value right here. This value is a temperature of 38 and a latitude of 48, let's say. I wonder if we can't figure out what that is. Let's see if I can't get to my U.S. cities. Let's see. Temperature of about 48, 47, and a latitude of 48. So if I can't find that easily. Maybe is it Los Angeles? Latitude. Oh, maybe it's Seattle, Washington. Maybe it's got something to do with currents or something like that. Okay, temperature is relatively high relatively low. No, that one's below. 26. I guess it must be Los Angeles, eh? Am I looking at it right? Coastal cities? Yeah, it could be coastal cities. Oh, you're still speculating what the other values are. Okay, I'm not gonna beat that to death. But now one of the important things about this is that I have data for the temperatures for 30 cities. Okay, now let's say I'm interested in knowing what the temperature is for a city that I don't know. For instance, say Elgin, Illinois. Okay, now I'm going to guess that Elgin, Illinois is at a latitude of about 40 degrees north, right? So now if I know what the latitude is, I can take that latitude and I can say, well, the temperature is equal to 110 minus 2.15 times my latitude of 40. So my average temperature is 110 minus 80. Let's see, I'm going to 0, 4 is 2, 6, 8, 86 is equal to 110 minus 86 is about, let's see, 10, 34, I guess, right? Is an average temperature of 34 degrees centigrade, I guess, 34 degrees Fahrenheit. Gets pretty cold there in the wintertime, 36 degrees Fahrenheit, 34 degrees Fahrenheit. So what I can do is I can use my regression formula to estimate or predict what my dependent value of my dependent variable is. Well, that's pretty important because that allows me to figure out, well, gee, I can make a lot of predictions based on this formula and my confidence in that formula that'll help me make judgments about what I'm likely to find when I test certain criteria. The other thing it allows me to do, it allows me to see that, well, the influence of latitude on a temperature is the latitude. Each degree of increase in latitude drops average temperature 2 degrees. Well, I may find that, well, what about elevation? What kind of effect does elevation have on average temperature? And I may find, well, for every 1,000 feet, that I may get a certain similar drop. Right? So I may be able to decide which of these two factors is more important to me in terms of predicting temperature. Is it the altitude or is it the latitude? Well, it's pretty trite to, for us to worry about which of these two are affecting temperature the most. However, let's say we're looking at this from a public health perspective. And instead of looking at trying to figure out temperature, that we're trying to figure out the rate, the rate of diabetes, right, in a population. And we're interested in knowing what the average rate of diabetes is based on a number of different factors. For instance, is the most important factor the amount of calories consumed? Is it the proportion of calories that are due to blood sugar that are attributable to sugars or starches? Is it the amount of physical activity? Is it the amount of education, and so on and so forth, right? So what that allows us to do is we can determine which of these various variables affects most, say, something like blood sugar or diabetes, and we can target our spending in public health to the factor that we think is going to most affect the likelihood of someone having diabetes. So we can use this power to predict or to observe what kind of effect one variable has on another to decide how we might use resources, how we might schedule interventions, and so on and so forth. Okay, so I just want to go through another one or two of these so you guys can see how this might work. I'm going to open up another set of data set. Okay, how about BMI and insulin sensitivity? Okay, insulin sensitivity is IS, BMI is body mass index, and let's see, I'm going to analyze. I'm going to go straight to regression. First thing I'm going to do again is I'm going to take a look, see if there appears to be any association at all. Okay, I'm going to go down to scatter plot, simple scatter plot. Okay, and which one do you think I want to put into my x-axis, and which is going to be my x-axis, my independent variable? Is it going to be insulin sensitivity, or is it going to be BMI? Which one is the one that's likely to influence the other? Which one's going to cause the other to change? I got an opinion on that? Yeah, I think so. I think so too. I think BMI is going to be our independent variable, and a higher BMI is going to make you more likely to be diabetic, or to be or to increase your insulin sensitivity. Okay, so I'm going to put BMI on my x-axis, insulin sensitivity on my y-axis. I'm going to plot it and see what it looks like. Okay, here's what it looks like. Does that look to you like it has a uh, 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 an association? Is there a correlation there? Okay, BMI, as BMI increases, insulin sensitivity decreases, in fact, right? In other words, the presence of insulin has less of an effect, right? So BMI increases seems to be associated with a decrease in insulin sensitivity. Now, based on what you saw before, do you expect your R value to be positive or negative? If I were to run a correlation now, you'd expect it to be negative. Would you expect it to be closer to 0 or closer to 1? Closer to 0 or -1? Okay, it's going to be negative. That's a tough one, isn't it? It's not a very good correlation, is it? It's certainly not as tight as a correlation as we saw before. Let's actually do it. Okay, now this is an important effect though. Even though the association is not as certain, this is an important effect that we're taking a look at here, right? So that has an enormous impact on public health. Correlate bivariate. Now, again, it's not going to ask me, because I'm just doing a correlation. It's not going to ask me for X and Y. Okay, let's see what we get. So our correlation, it's significant, right? 0.001. They're not independent of one another. There is an association between BMI and insulin sensitivity, but it's not as strong a correlation as we saw before in the two previous data sets. But it's a decent association, right? Now I'm going to do a regression, analyze, regression, linear. Looks pretty linear, right? Reasonably linear. My independent variable, again, was BMI. My dependent variable was insulin sensitivity. I'm going to click OK. And let's see what there's my R value is point. Remember, it ignores the negative sign because it's really using it to calculate R square. R square is 30%. What does that tell us about R square? What does that 30% tell us? That 30% of the variability in insulin sensitivity can be accounted for by the change in BMI. Well, that's not very much. That means most of the change in insulin sensitivity has other factors, right? And we're going to be eventually want to be interested in what those other factors are, right? But that next week we're going to take a look at situations where we're going to try and look at more than two variables at the same time, how more than one variable affects another, how multiple variables affect the thing that the variable we're interested in, which in this case is insulin sensitivity. So there are other factors that are having a big impact on insulin sensitivity. They might be the amount of exercise, they might be age, for instance. Age is going to be an important factor, and amount of exercise, diet, so on and so forth. All of these things are going to have an impact besides just BMI. Okay, but BMI has a decent correlation. So I'm going to take a quick look at this. And again, I see these coefficients, and I know that 1.6, 1.582, 1.6 roughly, that's my y-intercept. My x-intercept, my slope is negative 0.043. So what does that mean in terms of writing a formula for a straight line which describes this relationship. Okay, and I'm going to go back in here and I'm going to get a fresh page. Oops. Okay, and I'm going to give this a try. Let me move this up a little. Okay, what's my formula going to be now? My formula is going to be y is equal to, well, what's my formula going to be? It's going to be equal to this constant 1.6. I'll make it 1.58, right? Minus 0.043 times x. Well, my y is my insulin sensitivity is equal to 1.58 minus 0.043 times my x, which is my BMI. So if I wanted to use this formula to predict whether or not BMI, predict a person's insulin sensitivity based on their BMI, I just substitute, well, if a person has a BMI of 30, I would substitute 30 for BMI, calculate what this formula suggests their insulin sensitivity is. Okay, so now I'm going to show you some other stuff. Perhaps we'll get together during the week and I'll continue this and we'll take a look at some other factors that are involved here, such as how far, if we were to actually look back at these values, how far off each one of them are, how to deal with outliers and so on and so forth. I want to just talk very briefly about outliers. So we could use this predictively. Okay, this is not going to be as good a predictor as the other study that we did because our correlation wasn't quite as good. Okay, so now one of the things I want that somebody brought up before was we had a value that was pretty far away from all the other values. You remember when I drew this line to represent the formula, I mentioned the y is a very useful tool for us because it anchors that point. And then if we know what the slope is, we can draw that line. We may only really be interested in this section of it. This part might be, too high to be useful, too low to make any sense, and so on. We might only be interested in that part of it, but that y-intercept anchors that point for us. Okay, well, try to imagine this. You got that y-intercept, right? So now that slope is very important to us because that slope is a bit more important to us than that y-intercept is because that's just an anchor point for us, right? If we have a slope like this, that tells us that this factor, as this goes up, it has this kind of influence. This is the rate at which it causes our dependent variable to go up. If the slope looks going through the same way, if the slope looks like this, well, that factor has more of an impact. The slope is steeper, has more of an impact than this line does. This factor has more of an impact than this factor does. Okay, so that slope's important to us, right? So now let me take a look at that slope. What happens when I have an outlier? Oops. Okay, let's say this is our line right here, going through here. Here's a line going through here. Okay, I'm going to look at this as kind of a seesaw. In the middle here, there's a pivot, right? If I have an outlier over here, right, what's going to happen here? But if I have an outlier in the middle here, remember I'm only really working with this part of it. I don't really even look at this part, right? Not really using that for anything useful, right? If I have a point that's down here, it tends to tug at this from the middle, and it takes that line and pulls it down, right? Has a little bit of an effect on the slope, but it mostly just pulls it down. Remember, the slope is the part that's important to us because the slope tells us the relationship between factor 1, the independent factor, and the dependent factor, right? Now, let's take a look at what happens if we have an outlier up here at this end. Let's forget about this guy. If we have an outlier at this end or at this end, well, that has a tendency to pull this part of the line down, this part of the line up, and that has a tendency to affect the slope more than an outlier in the middle range of the x-axis has, right? So that's why we were talking about earlier in the lecture, that outliers to the far left and the far right are of more concern to us than, say, an outlier in the middle of this range. Okay, and next week, maybe we'll get a chance to work with SPSS, take a look at how SPSS also can give us a bit more information on what what the outliers are, and whether or not there may be issues with our data that cause us concern, such as, for instance, if we noticed that, gee, all of the lower value, all of the values that are a bit, we got a lot of values that are kind of like wacky over here on one end, but up here they're much more spread out. So the distribution of these, even though we wind up with a nice line in here, things are different up here than the way that they are distributed down here. So there might be some issues with our data that we might want to learn more about. But we're going to take a closer look at that next week. I'm going to put up maybe two problems. Maybe one problem is going to be how to use Excel or your calculator to calculate the R value. And the other problem is going to be using SPSS to determine what the formula for your regression is. So you can actually write the formula. Okay, so two simple problems, not too much work, not a lot of extra work and stuff like that, but something that will set you up to prepare for next week and kind of cement in what we did tonight. Okay, so good night, guys. We're running a bit late. Like I said before,